But this case, look, very simple. If you learn the electronics, you know this is the XOR gate. XOR gate means yes means no, negative, the two gate, XOR. And the positive get a negative. One negative, one positive always got a positive. Both positive get a positive, right? Got a negative. That's the XOR gate. Cannot be simpler than that. But if you draw it, you see, it's like this. They're diagonal. Now I want to ask you, this is just a two-dimensional. Can you draw any line to separate these two classes? You just can't, right? You either draw two lines or you draw a logistic curve like that. You can separate it. But otherwise, you cannot draw any line to separate this. In other words, the model we used before will not work, even for this simple case. Because this is not a linear problem. What means a linear problem? Linear problem always change proportionally. If the income for each business start to increase, my total profit is going to increase. That's linear in a way. And but like in here, we are both positive. Instead of more, it becomes less. Can you see? Right? That just broke the whole proportion sense, right? Both positive should be better than one, but it's negative one. So back into that. That's why it's the XO. XO. You cannot do it. So what do we do? Well, one way to do is got a multi-layer. That's a typical multi-layer. It's not one layer. And then you can see there's much more weight functions. Here, we got a more than 6, a more than 5. That's 15, 18. You got 18 of those weight. And to get a little more challenging, because all the learning you got is one layer here, one layer here. You don't know anything about it here. You see? And then each time from this weight, you got to estimate here as pretend you get some output here to look at this layer. Or put this as your input, pretend this is the layer, then can you train this. But that's called forward, if you just go forward. But that's all different algorithms beyond what we can talk today. But that will solve the problem. So in that type, we can look about not just a constant t. We can look at a linear function, a logistic curve. That's most frequently used one, like our memory, like our performance, you know, and logistic, like the money accumulation. So now go back to the problem of this XOR. See, we only need 2 lines to complete, right? And then, you know, in the between belongs to the negative, and the two outside become negative. So you get to build this network to do the work, to finish this non-linear model. But now, we not only just the deep, Google's deep learning, you can get a lot, as they said, many, I don't know, I forget, many layers, not just one layer, because the power of the computation is much bigger than 10, 20. But the same formula, the goal is the same. You want to minimize this error, right? That's when in statistics, when put a hat on the top, that means it's estimate. It's a hat. The hat is estimation. That's what you know. And you always need to minimize this least square, you know, called the square, sum square. Well, the real difference is this function. How do you estimate it? And what we see a moment ago is just a linear function, a dot product. It's just a plan. If we only have 2 variables, that's this surface. You all know this in the Cal 3. That's a dish, or call it circular paraboloid, just like a dish. You always have the bottom here, right? To get this bottom is very simple. Take the partial derivative, set it equals 0. That's a linear equation, you solve it. And then you found the bottom. But that's not so simple. One, the estimate functions are not linear, not just the dot product. If you involve other, like square, we call it quadratic function. If you get a quadratic function, when you square it, it's a fourth degree, right? If you get the fourth degree, your curve, for that square, the fourth degree, you can have a minimum, you can have a multiple peak, multiple value. And then your algorithm could use so-called descendant, like a hill climb, to find the bottom. But you find the bottom, that's the small bottom, not the big bottom. Or find the hill, that's not the real hill. The real big hill is on the other side. Then you have all those problems in the mathematics and research. And then now, currently, we got this so-called deep learning architecture. The deep learning architecture has multiple layers of neural network. Think about the naive Bayesian. Naive Bayesian method basically is no memory. It's memoryless. You just make a shot and then get what you have and then compare. That's called memoryless. If you look at the Markov chain, in the time series, the Markov chain, MFARKEV, this is a very popular model. That chain is a one-step memory. Whatever my action, always related one state of memory of my last time memory, and then a stimulus outside. Then I make my action. And that chain, in the outside level, you only can see their behavior. You cannot see what's inside the calculation. But the machine keeps the one-step memory as a state machine in the time series. In each time I remember the last time memory, but I don't remember the history memory, long memory. But if you get the memory a little longer, of course you're smarter, right? But the complication will be very big. So all those associated memory, they have to be somehow shallow, but you can extend the one step, two steps, three steps. If a robot can have 3 steps memory, that's a very smart robot. Okay, that's a kind of one challenge. The deep network have 2 things. This architecture difference to the traditional network. One is a hierarchy level, and the second is the memory steps. So this is another startup. And in 2010, 4 people in British built a company called called DeepMind. It's an artificial intelligence company, and the company's goal is really simple: play games. Play those old games, video games, and all the games they try to exceed. And at the end, what's Deep Blue? Those are the huge machine, have huge memory behind it, and beat the human being in the Jeopardy in the first time in 3 years ago. And then this company claimed, and my computer can play games. Computer can play the video games. There's one game still computer did not beat the human, is the Go. The Chinese, Japanese play this game, just the white stone and the black stone with a huge board. And they played the Go and did pretty well and win the case. They got the best company award in 2014. But after 4 years, Google bought it. The original price is 400 million. That means each of them in 4 years got 100 million, but actually it got more money. They got 500 to 600 million. Neural network is the best for parallelism. You can, like the IBM Watson, they have thousands of computers parallel computed, and in the end it's a voted result. If the answer is right or wrong, they have probably thousands of computers concurrent running, hundreds of computers merged the final result, and the hundreds in the end vote what's the right answer, and the majority win. because each of them followed a different algorithm in different way to solve the problem. That's how they win the case. You see, the massive parallelism, that give you also the advantage. Think about cloud computing. And this is so-called crowdsourcing. The people use massive data to give them the intelligence. You know, if everybody could get error, but the massive people won't get it wrong. As I showed you the example. If you ask millions of people what's the population for a small country like Thailand or Belgium, everybody could be wrong. But if you accumulate them, look at the mode, the median, and the average, get very close.